Okay, so white dwarf has that limit of 1.4 solar masses. It's called the Chandrasekhar limit. I know, right?
How do you say that?
Is that an R?
Chandrasekhar. Yeah.
Oh, it looked like
Saker.
E for a second.
And then this is kind of, there's a lot of stuff in physical science that seems backward, and this is one of them. Okay, like if you're talking about a white dwarf, the more massive it is, the more massive, the WD stands for white dwarf. The more massive the white dwarf, the smaller its volume, which seems kind of backwards. But it kind of makes sense because it like piles in, and that's actually why you can't get a certain mass or you're in trouble. Then the nova thing, I actually have a little picture up here at the top. And here's my picture of the companion, red giant, okay. The little star thing there is a retired white dwarf. And so actually nova, I wrote in purple, they can reoccur. And so nova kind of happen on the accretion disk. Nuclear fusion just kind of kicks in with that hydrogen fusing to helium. So that's a nova. And then pulsars are showing us that there is a neutron star there. It's a repeating, very fast energy blip, I said, and it's coming from it's coming from a rotating neutron star. That's what a pulsar is. And the two types of supernova. And so for the first one, I'm actually going to refer you to the little picture at the top there. Okay, so for the type 1A, you have a white dwarf being dumped on by a swollen giant companion, like it's up there. Okay, but I go on to say the thing that's different between the nova and the supernova 1A, I have it in blue up there, but material dumps on the white dwarf. In fact, the white dwarf nears that Chandrasekhar limit of 1.4, and then nuclear fusion suddenly begins in the core and it blows up. Sad face. So nova and a type 1A supernova have very similar sort of situations. And then the type 2 supernova is that massive star. I think we put like more massive than 8 times the mass of our sun. It's in its core, it's fused silicon to iron. And I didn't talk much about this, the explosion part, but with iron in its core, the core stiffens and it explodes. You don't need to know if stiffens, but I like that word. And then for gravitational redshift, I brought in a little picture down there. So with the 3 little pictures of that person who's dangerously close to that white dwarf, okay, so the white thing's a white dwarf or a neutron star, and we end up putting a light far away, closer and closer, and so gravitational redshift is basically the light trying to, the closer the light is to the object, the more the fabric of, I said that basically the space-time is curved, so it has to fight its way to get out. So light loses energy as it climbs out. It's gravitational redshift. And then if that weren't enough, the whole Einstein thing, so actually on 2 slides, after we talked about the assumptions, we said that something happens with regard to your length, okay, with regard to time, and with regard to mass. So the 3 colors up there are how you're affected if you are in the frame of reference that's moving fast. Things will look fine to you, but if somebody is not moving fast, like the rest of your family, no, they will see your length shorten, and they'll see time go slower for you, and they will notice that your mass has increased. And then, oh, I see, I need to add something. Then I have black holes in general. There's more than just this way to get a black hole. But black holes, what they have in general is a singularity in the middle, and the dot, dot, dot is the event horizon. And then, of course, they have that Schwarzschild radius. And let me add something. So that's kind of the anatomy part. But I need to address this thing about escape velocity. Okay, what it means is if you are escape velocity, how do I say this? I'll put it in so many words over here. Escape velocity. I'll say if you're within the event horizon, okay, you'd need to, I'll put it this way, you would need to go faster than the speed of light, and that ain't happening. I'm just going to put then c, that's the speed of light, to escape. Oops. Okay. Next chapter, terms. So this is where we talked about the Milky Way. And so you'll need to know kind of the general anatomy, and that's a photo from your textbook. Well, it's not a photo, it says figure, right? Because we really can't see that in our Milky Way galaxy. But that's kind of what generally our Milky Way galaxy looks like. So the little check marks, you should know the term disk, of course, halo region. I put bulge is the center. Sometimes we call that the nuclear bulge.
Well, I guess I'm confused because I just thought the bulge and the halo were the same thing.
Nope. I'm glad you said something. Nope. The bulge is kind of right there.
Okay, and then the halo is what you see up and around.
Exactly. The bulge goes through the disk is one way to kind of think about it.
Okay.
Sometimes called a nuclear bulge. And then the other thing, must be a question on there about kind of some dimensions. So in purple there, I kind of highlighted some dimensions. So, you know, like it's, I guess this would be its diameter, right? It's about 100,000 light years out at the edge, because it gets thinner, right? It gets thickest at the bulge, it gets thinner, is 1,000 light years. And our sun's location is about, well, you know, if you figure it's 100,000 light years from side to side, its radius is 50,000. So if you take 50,000, divide it in half, you get 25. It's about 27. So. And then I went ahead and brought in a picture for the next one because I think that is so cool. How and we talked about this last week, how like the yellow would be, oops, pause. Whoa. The yellow would be the disk stars, and the green are kind of like the halo stars. You can see it very good. So the disk stars are orderly, that yellow, and the halo stars are kind of random, the green. And so for the next one, do you guys remember this up here? These are all like looking at the Milky Way in different wavelengths. Okay, so the beauty of why do we look at in radio waves to gamma rays, we are able to see through the dust of our galaxy, and I didn't emphasize that, but that's why we do it. Now you can see if I make it bigger. There. You can see it better. That's all the Milky Way. That's like the Milky Way, but all we see is this. So there in orange, I put, we see through the Milky Way using at various wavelengths. And the next two kind of go together. There's a difference between stars that are in the disk and stars that are in the halo region. And in general, disk stars are what we call metal rich, and halo stars are metal poor. And actually, I brought in a figure down here at the bottom to kind of emphasize that. You can't see it very good. That's actually the Milky Way, and that's the bulge, and so we're right back here. But it says disk stars they have 2%, which doesn't seem like much, but it is. And then halo stars don't have much. And then the other thing kind of related to that is this idea of old versus young stars. And it seems backwards to me, but population 2 stars are old stars, and population 1 stars are young stars.
The younger stars are in the disk, right?
Right. Mm-hmm. And that Sagittarius A star, the thing about that is the very center of our galaxy, Sagittarius A star, and it's a black hole. So if anybody talks about an object called Sagittarius A star, and here in orange I said, why do they call it Sagittarius A star? Why not Orion A star? It's because it happens to lie in the constellation Sagittarius. And then one last thing, and I had to correct, I see a typo here. Instead of hole, it should be how. How do we know there's a black hole in the center of the galaxy? And in blue there, the two things that gets us to the idea that that our galaxy has a black hole in the center of it is we needed to know its mass. And so in blue there, I said we got its mass by tracking stars as they move over years. Okay, so if we have its mass and we know its volume just by, we know volume, okay, then actually in green there, I say you know that the mass is confined to that volume. So as I've been kind of stomping on, okay, you know that you have you've gone past neutron degeneracy and you must have a black hole. And it's all about density. It's kind of like that crazy man on the video said, took a piece of paper. Okay? So then this is stuff we're going to get to tonight. Okay. First one's pretty straightforward. They're all really not too bad. As I was getting the test together on Tuesday or whatever, I don't think it's too bad. So when we talk about galaxies, we're going to talk about, although there are kind of like little nuances to galaxies, but what I really want you to know is spiral, and then barred spirals, and then elliptical galaxies. I don't know if you remember, do you guys remember which one our Milky Way galaxy is? Is it barred spiral? Mm-hmm. Yep. So if you think of our Milky Way, it's got those cool arms, okay? And we're going to see actually there's a relationship between how tightly wound the arms are and its nuclear bulge. And it kind of makes sense, because like as I tightly wind my arms, as I kind of scrunch down like that, what happens is the bulge actually gets larger. So the more tightly wound the spiral arms, the larger the nuclear bulge. So when we talk about spirals, galaxies, there are, we talk about a sub A, sub B, sub C, and it has to do with how tightly wound the arms are. Okay, the next one, I think I've been telling you that it wasn't until 1923 we understood the concept of a galaxy. And actually, that's what that third line is. In 1920 something, 21, I'm not sure, 20? Well, there was a debate about something called the Andromeda how far away is the Andromeda Nebula / galaxy? Okay, so actually they didn't know it was a galaxy until Edwin Hubble found out how far away it was. Okay, so what he helped resolve was how far away the Andromeda galaxy is. We know it's a galaxy, but they didn't know it back then. And then in gray there, we'll be talking more about there's no way you can visit these galaxies. How do you know how far away a galaxy is? And in gray there, I talked about something called a standard candle, and we'll talk about that more. But basically, he used a type of star called a Cepheid variable star. Cepheid variable star. The word variable might kind of give it up. Do you remember when we talked about giants, how they kind of move around on an HR diagram? That's the variability we're talking about. Giants, when they're kind of going out, they can swing up and down. That's variable. Okay, so the Cepheid variable he used as a standard candle.
Standard what?
Standard candle. And I see here, in a minute, I'm going to have to explain standard candle in a consent, in a little way. And we'll
Is that C, it says he figured this out by using a what? A C?
Cepheid, so it's CEPH. Cepheid. Variable. And then, like the next one, I think we've been talking about that since the beginning of the class, it seems like. So since, galaxies are sending us light, but it takes a certain amount of time. I say it takes light a finite or certain amount of time to get to us from a galaxy. So the light we see from a galaxy left a long time ago, when the galaxy was younger. That's kind of a concept, we kind of come full circle. And that's how far I had time to do in my office. So, standard candles. Well, Hubble used them to understand how far away the Andromeda galaxy is. But basically, standard candles. We know how bright, let me change that, how luminous, because there's a difference. Luminous certain objects are. Okay, thus they are I'll just say equals standard candles. So Cepheid variables, they knew how bright it is. Oh, and let me go ahead and say one more thing, because this is going to come up later. So you compare brightness, which is what you see, with known luminosity, the standard candle, to get distance. And I'll go ahead and you guys don't have to calculate any of these, but it's probably gonna look familiar. You probably put it on your note card last time in a different way. Distance, as it turns out, is equal to luminosity divided by the square root of 4 pi brightness. So one more thing before we go on to the next page. Luminosity, this is standard candle. STD for standard candle. Hopefully it'll make even more sense tonight. Okay, so Hubble's law, I don't have these, so like I said, I'm going to have to kind of punt.
That's also chapter 16.
Yeah. Hubble's law says that the more distant the galaxy, I think we might have run into this before, the faster it's moving away from us in general. There are some miscellaneous galaxies that are moving toward us, but most of them are moving away from us, and the more distant the galaxy, the faster it's moving from us. Estimated age of the universe, and this is going to take some explaining, okay? But from Hubble's law, there is a, let me do one more thing with Hubble's law. Tonight, you're going to see a nice little scatter plot for Hubble's law, and it's going to look like this. And along the x-axis is going to be distance of galaxy. And along the y-axis is going to be what we call recessional velocity, which basically means how fast it's moving from us. Recessional V, okay? And here's the scatter plot part of it. Scientists love scatter plots. So basically, each of these dots represents a galaxy farther away from us, going faster. And so this, in a nutshell, is Hubble drew a straight line in there, and actually, there you go. And so I mention that because actually from that plot, he used it to estimate the age of the universe from the slope of that. So, bottom line, what you need to know for the test is it's 13 to 15 billion years old. B stands for billion. Bottom line. The next one, oh yeah. So, you saw up above there that the farther away the galaxy is from us, the faster it's moving. So, do you remember this idea of redshift? If something's moving away from us, if it's sending out a signal, the signal it's sending, the wavelengths are lengthened, redshift. So here's the deal. What we notice is that, how do I say this? Recessional motion, I'm going to say increases. I heard that buzz. Increases with distance. Okay, and as recessional motion increases, then the redshift you see also increases. So galactic redshift increases with distance. Because the redshift is created by something moving faster, and if it's moving faster greater distances, it's got more of a redshift. Okay. So we'll talk about that tonight.
They like red and blue, don't they? And, one time it's something else, and it's very confusing.
It does. I can tell you've been reading your book. And this one, let's see, trying to catch the changes in a galaxy over time is kind of like, how in the heck do you do that? But basically, we look for baby galaxies far away. How's that? Look for baby. Aw. Far, far away.
So not all of the galaxies were born at the same time, or developed, or whatever the hell the word is, at the same time then?
Right. Seems reasonable.
I was just assuming, I guess, that what falls
kind
in
of-
there.
Yeah. But you figure if, like, we look far away and we're seeing baby pictures of stuff, then to see the old galaxies, I guess the mature galaxies, we just look close to us. Does that make sense? Okay. Put mature galaxies closer. It's weird to think of what we see versus what it really is.
I know, that's why I'm
So-
saying, like the red and then blue and then this, the
Yeah.
other. You would think that it would be the opposite.
I think I've heard that before, yes. And I try not to think about it too much, but
I'm
yeah.
not, 'cause I'm gonna,
No, I know. But I think that, to me, even though that looks like a really immature galaxy so far away, to me, it has, if we were there now, it would be the same as our neck of the woods with regard to maturity of galaxies. So, like, oh, so confusing. Proto-galactic cloud, I'm thinking you guys are, if you think you know it, you probably do. It just means an early on cloud. Let's see, how do I say this? Beginnings, an early on cloud. Beginnings of a galaxy. Let's see. And then the next one, and I'll probably bring in a picture for this. I'll probably redo some of these for my official video or whatever. But it's kind of neat that early on, and the galaxies were really, really close. And this kind of gets back to you. So I'll put early galaxies were close, physically close together, and interacted lots. We're close together with lots of interaction. Cool. The next two actually go together. Let me tell you what a quasar is first. I noticed in my notes it's kind of backwards. I don't really say what a quasar is. But a quasar is, it's the black hole in the center of a galaxy that is feasting. I'll put galaxy black hole, galaxy central black hole. Because we think most galaxies have black holes
it
in the
won't
middle.
be necessarily in the center, will it?
No, it will, because these
It
are
will?
these are the bit. Yeah,
Okay.
yeah. There are other black holes in a galaxy, probably, but then there's a supermassive black hole in the middle. And those these other black holes, they came from stars blowing up and stuff. These are called stellar black holes, like when a supernova type 2 sort of black holes. And then there's the supermassive black hole.
And that's what this is.
That's what this is.
Okay.
Yeah. Galaxy central black hole feeding. That's what a quasar is. And I'm going to go ahead and add to that, as you probably already figure, quasars are very energetic. Very energetic. So kind of related to that, directly related to that, we say that a galaxy is active if it's got a quasar going on. Active galaxies, and I'll go ahead and just say, well, I'll put it this way, active galaxies, black hole is feeding. And you're right. I'm talking about that middle one, the supermassive black hole. Yeah, isn't that it?
Every galaxy has a black hole
Mm-hmm.
right in the center.
Mm-hmm.
Um,
They used to
I
not.
guess that would make sense because all the energy would.
Yeah, and kind of like what they think that actually when galaxies form, that is a part of their forming, as they got that central thing.
Well, everything wants to suck to it.
No.
Huh?
Uh-huh.